Question 3. Right. The diagram shows an experimental setup that can be used to verify Newton's law of cooling and to determine the specific heat capacity of a given liquid. It consists of a calorimeter with a lid and a stirrer made of copper. Heated water, thermometer, and a stand to hang the calorimeter setup. An experimental procedure similar to the method used in the standard experiment is performed by keeping the setup closer to an open window of the laboratory. Right. In the standard experiment, what we use? We use a fan. In the standard experiment, we use a fan in front of this. Right. In the standard experiment, we use a fan here. Right. Now, without using the fan, now in this given experiment, so what is given is it is taken close to the window of the laboratory. Right. Then if there's a uniform wind flow, that is going to be correct. But if the wind flow changes, there are errors in the experiment, then we do so. Right. The advantage of doing this experiment near an open window where you get a slow uniform flow. Slow uniform flow right? If it has a uniform flow, that's fine. Right? If it has a uniform flow, that's fine. Wind is that you can verify the validity of Newton's law of cooling for higher temperature differences. Right. A. What are the readings you would take in the experiment to verify the Newton's law of cooling? Right. So what we draw is we plot a graph against time with temperature, no? Time with temperature, right? Then we need the temperature fall. We need the temperature fall with the time, right? Then first reading is, what are the readings? Then first reading should be, we need the temperature of the liquid against time. Temperature of the liquid against time or during same time intervals. Time intervals temperature of liquid, temperature of liquid during same time intervals. During same time intervals, right? And the second one, right? Obviously, we need room temperature. We need room temperature. Room temperature. Room temperature, right? What is the experimental procedure to be performed which enables you to reliably assume that the readings of the thermometer is same as the temperature of the outer surface of the calorimeter, right? We have to stir well. Right? When stir well, a uniform distribution of temperature is ensured, right? Then only option we got is we have to stir well, right? We have to stir well, right? Well stirring water, well stirring water, Right. 3. Draw rough sketches of the two graphs that you would plot to verify the Newton's law of cooling. Label the axes properly with appropriate units. Right. So one is we plot theta against time. No. First graph theta against time. Then theta is in degrees Celsius and time is in seconds. Right. If you plot this, right, what we get is something like this, starting from a temperature and it cools down until room temperature. Right. Graph starting at a temperature and cools down until room temperature, right? And another graph we can plot is to verify this, and another graph we can plot to verify this is, right? We know, right? Let me explain this a bit. So we know from Newton's law of cooling, Q over T is EA, theta minus theta. No? Q can be written as ms theta. Q is ms theta. Then ms theta over T equals EA theta minus theta. Right? Now, for a given liquid, if we plot theta over T, right? Theta over T is rate of cooling. Theta over T means rate of cooling, right? Theta over T is rate of cooling. Theta over T, right? For a given one, EA over ms is a constant, then this is theta minus theta, right? See what happens if we plot this against theta minus theta r and rate of cooling y equals mx. Then other possible graph is y equals mx. Y equals mx between theta over t, right? It should be measured in degrees Celsius per second, CS minus 1 degrees Celsius per second, right? With theta minus theta r, that is in degrees Celsius. In that case, we'll get a y equals mx, right? These two are the two possible graphs to verify this. Right? This graph is very popular, right? This graph is very popular, and this is the exact graph we plot in the experiment also, right? And about this graph, you have some kind of a additional thinking, a small thinking. Right? Part B. In order to determine the specific heat capacity of a given liquid, the same procedure used in A above is repeated for the liquid after obtaining relevant readings for water. Right. After obtaining relevant readings for water, now the liquid is added. So we know how to do. For the same calorimeter, we have to first remove water and have to add the liquid to the same calorimeter. Right. First question. What is the reason for using the same calorimeter used in part A to perform the experiment? When same calorimeter is used, E. What is E? E. Coefficient of emissivity. Coefficient of emissivity depends on nature of the surface. Nature of the surface remains constant, remains unchanged. To keep nature of the surface of calorimeter remains unchanged. To keep nature of the surface of calorimeter remains unchanged. Right? That's a common question. Experiment and that's a popular thing in the experiment. Second one, in addition to using of same calorimeter, what is the reason for using the same volume of water and liquid in the experiment? Same volumes of water and liquid. So what happens is, we know when this is in the calorimeter, right, we have to keep these areas. To address this area open to atmosphere in law of cooling. Area open to atmosphere, right? Now, when this is filled up to the same height, area open to atmosphere is going to be equal, right? Area open to atmosphere is going to be equal, right? Then purposefully we have to fill it up to the same level to keep A constant, right? Then the answer is to keep areas open to atmosphere. Of water and liquid, and liquid equal, to keep areas open to atmosphere of water and liquid equal, right? Because what we do in the experiment is, if I quickly explain here, we know law of cooling is Q over T equals EA theta minus theta R, no? Right? Law of cooling. Now, Q is ms theta, right? Q is we're gonna expand karna to E is constant, E is constant since same calorimeter is used. Then E is constant, E is addressed. A is constant because both liquid and water is filled up to the same level. And theta minus theta R should be constant because we are doing the experiment in the same temperature range. If all the right hand side is equal, Q over T should be equal, no? Then finally we can equalize Q over T of water with Q over T of liquid. That's why we try to keep EA and theta minus theta R constant, to keep that right hand side of the equation constant, right? That's the basic behind this, right? Next, part 3. the mass and specific heat capacity of the calorimeter with the lid and the stirrer are M and M and S respectively. Mass of specific heat capacity of the liquid are M, L and SL respectively. The average rate of loss of heat and the average rate of drop of temperature of the calorimeter with the liquid for a given temperature range are Hm and theta m respectively. In terms of these quantities, write down the relationship between Hm and theta m. But about the liquid now, so about the liquid we can say Q over T of liquid. See, Q over T of liquid equals Q over T of liquid equals, right? Q over T total there are two things in the system, calorimeter and the liquid. Then calorimeter absorbs some heat, right? Calorimeter, one second. Okay, right. Listen, so calorimeter uh, absorbs some heat, calorimeter liberates some heat, right? And at the same time, the liquid also liberates some heat. Calorimeter का heat को liberate करना, liquid liberate करना, because initially we are starting at a higher temperature and let the system cools down, right? So both liberates heat, Then this Q has liquid के लिए क्या this is liquid plus calorimeter. Then we have to mention both of them. For the liquid, that is ml SL. For the liquid, ml SL. For calorimeter, mass is given as m no. Then m and s. How many right? And temperature difference, say delta theta over T. How many? Now plug this using these given terms. What is HM? HM is the the average rate of loss of heat. That is Q over T. Then this is HM. This should be HM. Average rate of loss of heat. Make convert terms. Then this should be HM. This is HM. Then these terms are given ml SL plus ms, and again the average rate of drop of temperature delta theta over T is given, that is theta m. That's it. That is theta m. Average rate of loss of temperature is given, no? Theta m. Average rate of loss of temperature is given as theta m. Right? Directly you can use theta m. Right. Next. 4. Let m equal 0.15 kilograms, S 400, and ml 0.25. For a certain temperature difference, the average rate of heat loss of calorimeter with water, was found as 90. The average rate of drop of temperature of calorimeter with the liquid for same temperature difference is 0.125. Determine the specific heat capacity of liquid. Right. Now, this is where you have to use this logic we had before. Right. One kalnu Q omega. Since Q over T equals EA theta minus theta R in law of cooling. Right. Now, purposefully, what we do is same calorimeter is used. Then E can be kept constant, and both liquid and water filled up to same height. Filled up to same height. Then A can be constant, and to make this constant, all calculations are done in the same temperature range. Right? Now, when all three are constant, Q over T must be constant. If all three in right hand side are constants, Q over T must be constant. If all three in right hand side are constants, then Q over T must be constant. Since Q over T is constant, right? Simply Q over T of water with calorimeter equals Q over T of liquid with calorimeter. Liquid with calorimeter. This is the logic we will be using here. This is the logic we will be using here. Right. Then let's apply it here. Let's apply it here. Right. Then HM is given, no? Now simply HM is given. Water ke dunna kaman hai. Even if that is given in water, Q over T are equal. Right? Even if that is given in water, Q over T are equal. That is what we just proved. Q over T are equal. Then HM can be used as 90. Right? That is 90. Then 90 equals ml SL. ml, mass of liquid. Mass of liquid 0.25. 0.25. Right? Now we are going to find SL, no? SL plus MS. M is 0.15. 0.15. And S is 400. 400. Right? And temperature of is 0.125. Nikam meri dan tin 0.125. Right? Now a small simplification. Right? A small simplification. A small simplification. Right? Then 90 over 0.125. 90 over 0.125. What is simplification? 90 over 0.125 equals 0.25 SL plus 15 times 4 is 60. Then 400, 0 to 0 cancels. This is 60 again. 60. 15 times 4, 60. Right? Then I have to simplify this. SL equals 90 over 0.125. 90 over 0.125. Right? That should be divisible. That should be divisible. Let's see. 90 over 0.125. Right. Cancel it. Cancel. Let's cancel this. 90 over 0.125. This can be written as, right? Now, means if I get another 90 over 0.125 is 900 over 125. And 10 to the power, 10 to the power, measuring in minus 3, then minus 2. No? Sorry, plus 2. No? Then 125 and 900 kilogram by 25 by 25 times 5 here. This is 25 times 400, then 36. 36. Is it? Over 36. Then 36 over 5 kilogram 7.2. That is 720. This is 720. It is divisible. 720 equals 0.25 SL plus 60. Then 0.25 SL equals 720 minus 60 kilogram 660. 660, right? Yeah. Then SL is 660 over 25 10 to the power 2. Right? If this is simplified, the exact answer coming is 2640 joules per kilogram per degree Celsius or per Kelvin. Per Kelvin දාන්න ඕනේ. මොකද temperature එක දීලා තියෙන per Kelvin නේ. Then you better mention it in kelvins. So final answer